Let's start up a completely new situation and work all the way through the claim and trying to prove our point or fail to prove our point. Right here we see an old bag of Chips Ahoy, and up on top you'll notice that it says 1,000 chips in every bag. Now, whether or not that's true is what we're going to be figuring out, and we're not going to check to see that every single bag has exactly 1,000 or more. We're going to check that at least on average they have 1,000 chips or more, that they're not ripping off the customer. We could also look at whether or not they have too many chips. Maybe I'm health conscious and I'm worried that there's 2,000 chips in the bag or 1,500 chips, something like that. And so I, as the researcher, am curious if it actually is an average of 1,000 chips or if it's something different, something higher or lower. So as a researcher, when I'm asking myself questions like that, I set up my null and alternative hypotheses, and then I go out and collect some data. And the 17 bags that I bought from the store, I bought them at random stores, chose random packages, and found this many chips in each of my packages, and we'll use that as we get farther on. So let's go ahead and work through all our questions, same questions we used before. Let's start out with what is the claim? The claim is what we see on the bag. The claim comes from someone else, and that's that there's 1,000 chips in every bag. The average number of chips is 1,000. The researchers thought that's going to be that it's different, that it's not 1,000. So we're not saying that it's more than or less than, we're just saying that it's not 1,000. We'll talk about how to do that. Third question is, if we were to go out and challenge the claim, what question would you ask the individuals? Well, the individual in this case is not a person but a bag of chips. So we would ask each bag of chips per se, how many chips do you have? And the bag of chips probably wouldn't talk to us. We would actually have to open it up and take the cookies apart and count up all the chips. So we would have to investigate that way. Now getting into a little more detail here, it says what type of data are we dealing with? When we say how many chips, we're dealing with quantitative data, and quantitative data is summarized with a mean. So we want to look at the average, not the proportion. The null hypothesis then is going to be that mu is equal to something. The null is always a statement that something is equal. The mean or proportion, in this case, it's going to be the mean. So we're going to say that mu is going to equal the 1,000 chips, and we want to be specific of what we're talking about, so we're going to put a little subscript on mu and say mu number of chips, and that average number of chips is going to be equal to 1,000. So 1,000 chips per bag is the claim. Now the alternative is where we take the exact same statement and we make a copy of it, and then we change one thing, we change the symbol. So instead of saying they are equal, we have to decide, is it going to be greater than, less than, or not equal? Going back to the statement we made, we didn't say it's going to be smaller or larger, we're just going to say it's not 1,000. So we will use not equals in this case. So that is our alternative hypothesis. Note here, if you're curious about these symbols, H0 and HA, these are just different ways, different shorthand for saying null hypothesis, alternative. The null being 0, alternative with a little a. Now we need to decide our reasonable alpha value, our cutoff point, and we always say that that's going to be 0.05 unless we have a reason to say otherwise. A good reason would be something like if we're going to accuse someone else of doing something wrong, and we're going to make a public statement, we might want to be a little bit more than 0.05. So if we're just testing this for our own purposes, this is fine. If we're going to publish this, we might want to even lower that value a little more just to make sure that we're not slandering anyone. What test and stat key will you perform? We're going to use the test of the mean. Reason for that is that we are dealing with quantitative data. Now we're going to look left tail, right tail, or two tail. We're going to look two tail because we have a not equals test. We're not looking lower, we're not looking higher, we're looking both. So we need to do a two-tail test, and we'll practice that in a moment. Last one says what assumptions do you need to make? We need to check them. We need to make sure that we have an SRS or equivalent. And in this case, we said when we went out to collect all of our data that this data came from taking a random sampling of Chips Ahoy bags at the grocery store. So it is in fact a random sample. Now the p-value, that's the hard part. That's where we need to actually do our calculation. So if we go over into StatKey, we're going to look for our test of a single mean. And once we open that up, we're going to edit our data and paste in all of our values. Note that this data is available to copy and paste just below this video. Once it is in there, we also need to set our null hypothesis. It already tells us that mu is equal to something because every null hypothesis dealing with means is going to be mu equals, and we want to say 1,000 chips, so mu equals 1,000. Once that is all in there, we can start generating our resamples, our bootstrap samples. And you'll notice that in the middle you'll see our null of 1,000, and then it generates a curve around what we would expect to see as different sample averages if we were to do this many times over. And so we see a reasonable amount of different sample averages, and then we see the mean that we calculated here from our original sample, 1008.7 approximately. Now we said we were going to do two-tail because we did a not equals test, so this is going to be two-tail. If it was less than, it'd be left tail, right tail would be greater than. And we're going to adjust this slider right here to match our sample mean. So I'm actually just going to copy and paste that and paste it right in there. And then it will adjust both the right side and the left side will move as well. You'll notice that these two proportions end up matching up. That's how it decides how far to move the slider, is based on this proportion. Our p-value when you're doing a two-sided test comes from adding this number here, this 0.083, and the other side. Two-sided test, we have two shaded regions in red. We have to add them both together. So we take 0.083 plus 0.083 to get 0.166. So our p-value then, if we jump down here, is 0.166, which is actually quite high. So I'm thinking that we are not going to be convinced. It is not as high as our 0.05 that we were looking for. It is, or not as low, excuse me. It is too high. So we are going to not reject. And if we were to write this out in words, we would say fail to reject. The reason we use that language is we have not proved the null hypothesis true by any means. All we've done is failed to disprove it. Does this make our data statistically significant? No, it does not. Our data is not statistically significant because we failed to reject. If we had to state our decision in context to say what we're talking about, we would say that we failed to find a difference, or we failed to find that there were not 1,000 chips. Of Chips Ahoy. And whenever you're talking about context, you want to be specific. You want to say exactly what you're talking about. So we failed to find that there are not 1,000 chips in a bag of Chips Ahoy. We didn't prove that there is 1,000. So be careful with that distinction. Two questions on this page. It says if you rejected, if you failed to reject. We failed to reject, so we need to answer this first question. Was our p-value strong enough to warrant redoing a study with a larger sample size? Now this gets at the idea that if you have larger sample sizes, that's going to affect the curve that you have in StatKey. It's going to make that curve a lot narrower. And if that curve is narrower, the region in red is going to get smaller. And if that region gets smaller, your p-value goes down. So in theory, if you have a larger sample size, you're more capable of detecting a difference. So if our p-value is too high, but close enough, it seems like something's going on, it might be worth doing another test with a larger sample. Instead of doing 17 bags, maybe do 30 or 40 bags of chips and see if we can prove our point with a larger sample. So in this case, I would say maybe. If we really care, if we really want to prove the Chips Ahoy people wrong, yeah, we should go ahead and buy more bags of Chips Ahoy, take them apart, and get that data. 0.166 is not that convincing of a p-value, so gray area. Last question, it says, imagine you found out from a census of all the Chips Ahoy in the world sometime later that you actually made the wrong decision. It turned out that there were not an average of 1,000 chips in a bag. If that were the case, we would make a type 2 error. Whenever you failed to reject and you were in the wrong for doing so, you would have made a type 2 error.